So conservation of momentum is going to be actually very useful to answer many questions of physics and engineering importance. And in fact, it is true that the force required to hold a fire hose when it's going full speed there is quite different. It's quite a lot. Actually, I've seen some videos of firemen where the guy holding the fire hose is actually being kept in place by another fireman in the back that holds their back. You know, there's two firemen. One is holding the hose like in this picture, and the other fireman in the back is perhaps just keeping some slack on the hose and keeping his arm against the back of the front guy to help him withstand that force, because otherwise he would be pushed back. That's just conservation of momentum. We'll see how we can estimate that a little later. So before we do that, let's just specify the types of forces that are involved. Any firemen in the room? No? Anybody with experience? No? You have? So is it tough? You need two people, right? So I'm not making this up. It's true. Yeah. So now you will know why. So the types of forces that are involved in this Newton's law that we just discussed are basically gravity. That's no surprise. We have gravity, so it's going to be basically we have a mass. A small element of mass is equals to rho times the volume, and that's for a small fluid element, and so the force here is mass times acceleration, so the force is going to be equal to rho g d volume, and for all the fluid in the control volume we would have the force of gravity equal to the integral rho g d volume. Gravity. The other forces that we could have, forces of pressure. If we look at small elements of fluid, each one is going to be subject to some pressure, and then that pressure we will see a macroscopic result on a control volume by looking at the surfaces of the control volume. And the pressure is going to be the total force due to normal stresses, and we could write it the total force due to normal stresses or pressure forces equal to minus integral over now the control surface. It's a surface force, P n dA, where n is the outward facing normal. As shown in that cartoon. Yes? What did I say what was? N, outward facing normal. A unit vector pointing outward, that's why we have a minus sign, because the pressure always points inwards, the normal points outwards, so basically we've put the minus sign here so that we don't have to worry about, we know already which direction the pressure is acting. That's our surface force due to pressure, normal stresses. Then the third is shear stresses. Shear stresses at the molecular level can be seen in a macroscopic effect by looking at the surfaces of the control volume or wall shear stress. And so the total force due to shear stresses basically is the integral of the shear stress at the wall times this little s is going to be a tangent unit vector dA. And finally, we could have interaction with objects. Objects that are submerged in the fluid will act by pressure and shear, and there will be a total force that we can usually calculate, a force, for example, in this case, due to that pipe contraction. Any object that is in contact with the fluid will, of course, cause, again, a force. And the final force balance is integral rho g dv. This is the gravity force minus integral across the controlled surfaces of P and dA are pressure forces plus integral of, on the surface again, wall shear stress times a tangent vector dA, and finally some force of interaction with objects. Let's just call them, let's just leave this one force of any immersed bodies, IB immersed body.
Is there a reason why that?
No, actually there's no reason for that dot to be there because I've already, this is not a vector here. So yeah, good catch. Okay, so all of those forces now must equal the change in momentum for the fluid. So now let's present Bernoulli's equation, and with these, now we will have an overview after just this 50 minutes of lecture or so, an overview of the whole chapter, which is going to be based on conservation of mass, conservation of momentum, conservation of energy. Okay, I haven't covered that one yet, but Bernoulli's equation. But with mass, momentum, and Bernoulli, we can do a lot. So we'll take our time now to see how to apply these. And then we'll see energy, and then we'll have really a very complete tool set to solve problems of engineering importance involving fluids. So Bernoulli's equations basically has several versions and several derivations. We are going to see various different ways of writing Bernoulli's equation. And I don't want to, at the moment, show you any derivation. We will first use the equation, and then we will explain it using energy, and then I will give you some pointers on how one would actually derive Bernoulli's equation. But what's important, most important to know about Bernoulli's equations is what are the assumptions. The assumptions of Bernoulli's equations are that the flow is steady, so there are no derivatives with respect to time. These are all zero. The density is constant. We assume incompressible flow for the time being. There is a way to write sort of an extended version of Bernoulli's equation for compressible flows, but don't worry about that. The basic equation assumes incompressible flow. There are no shear stresses, so basically the fluid is inviscid, so viscosity equal to 0. No heat transfer, no work. So Q equal to 0, work equal to 0 on our thermodynamics. Basically, these three together are saying that the flow is reversible. This is a reversible situation. It's ideal. Okay? Bernoulli applies to ideal flow. But we'll see in many cases this is a good approximation. And for the time being, we will consider just single inlet, single outlet. There's a more rigorous way to discuss that, but we'll do that later. First of all, just consider single inlet, single outlet. For this, all of these assumptions, then we can apply the following equation. P1 plus 1/2 rho V1 squared, V velocity, plus rho g Z1, Z1 is C is elevation, P is pressure, V is velocity of the fluid, and this is a constant. So in one inlet, say 1, and one outlet 2, we would write P2 plus 1/2 rho V2 squared plus rho g Z2. So basically this is equal to a constant. We will explain this, interpret it, and sort of prove it later. But I don't want to do it right now because we need to do some examples so that you get used to this combination of principles first and how they're used in engineering problems. Otherwise, I will get you all really to sleep. And thank you for your patience so far. Now let's use this in combination with conservation of mass and conservation of momentum and see how they are applied. And later on, by the way, this was developed in 1790 or something like that. It's amazing how, at the time of the revolution, we're talking about, the times of the French Revolution, the times of the U.S. Revolution, plus or minus a few years, these guys understood so much about fluids and engineering fluid mechanics. Here's a picture of Daniel Bernoulli. He's Daniel Bernoulli. He has a brother as well, another Bernoulli that also contributed quite a bit to engineering. Okay, so let's do immediately some examples. So the first application that we can talk about, first common application of the principles that we've just introduced of conservation of mass, momentum, and also Bernoulli principle is for fluid jets. The case that we were talking about of the fire hose is one example where we might have something like this. A high-speed stream of fluid which is leaving a nozzle, which is pictured here in this cartoon at, say, location B. And so we have flow going in and flow coming out of a nozzle at some high speed. The most important thing here, the most important trick to remember is that this is called a free jet. And free jet, what it means, free jet, we use the expression free jet, and the reason we use that expression is because the exit is at atmospheric pressure. It's just open to the atmosphere, and therefore it is at atmospheric pressure. So because of this, the most useful tip that you can apply here is to use gauge pressure. Use relative pressure with respect to atmosphere, because then of course the pressure at the exit is going to be 0, and some of your equations will simplify. So use gauge pressure for all of these problems, any problem like this, when calculating forces. And so then we have, at the free jet, we have the pressure at B is equal to the pressure at C, and is equal to, well, 0. Gauge, 0 gauge. So that's our tip number 1. Tip number 2 is we can usually assume that the velocity is uniform across any cross section. So we're going to be able to, for example, apply conservation of mass, conservation of momentum, and so on. for this example. Let's look at a specific example for calculating the thrust of a rocket. Classical example of these principles. Okay, rocket thrust. So consider a rocket which is supported by a beam, like drawn here. So basically this is similar to the case, it's like a free jet again, okay? So we want to calculate, normally what we want to calculate, in this case the rocket is not moving, it's just being held in place by a beam, and we want to calculate the force on the beam. We want to make sure that this rocket doesn't just break loose, we want to have control over that, we want to calculate the force on the beam. So let's give this some numbers. So we have the exhaust jet, which is a free jet at atmospheric pressure from the rocket, has diameter equal to 1 centimeter. This is a little small rocket. The velocity is quite high, of course, 450 meters per second. And the density of the exhaust, which is hot air and burned gases, is going to be 0.5 kilograms per cubic meter. And of course, we want to find, in this case, the force acting on the beam. So we're going to apply momentum conservation to find the force. The first thing to do is to choose a control volume. And one of the most useful things to do is usually to look at your situation and choose a control volume that is perpendicular to the velocity so that we can obtain those fluxes quite easily. So let's choose a control volume that encloses the whole rocket, crosses here perpendicular to the jet, and at one point, of course, it's going to cut that beam. So we have some force here on the beam. We have a force here. Let's write it, force on the beam, which is what we want to calculate. We have, what do we have? We also have the weight of this guy, the rocket. That will be our force diagram here for the control volume. The force on the control volume is exerted downward, and the force on the beam is upward. So we're drawing the force on the control volume. So this is our first step, to draw the control volume. And then we look at the different forms. So what other forms of forces did we have? We had weight. We have the weight right here. We have a force because of interaction with a object, the beam. So we got that. Pressure forces. Okay, do we have pressure forces? Well, we actually don't have pressure forces because the exit pressure is atmospheric. It's a free jet. So free jet, then we have that is at atmospheric pressure. And if we use gauge pressure, it means that pressure is everywhere zero. Atmospheric pressure everywhere. So we don't need to consider any pressure forces in this free body diagram. And the other one was shear stresses, but we don't have any shear stresses either because this is not moving, there's not rubbing against anything, there's no friction against anything, the jet is free, it's just, coming out of our control volume with no friction. So that's all we have. Okay, control volume, and we chose the control volume, drew our forces. We're ready with that. Second step is look at the momentum. We can actually do a momentum diagram similar to a force diagram. So let me draw again our control volume here. We have the rocket inside, right? And we have the rocket and the beam. We have basically that this is the only momentum, m dot v here. That's it. So we have only one momentum component. So now we use the momentum equation in the z direction. And we have sum of forces in the z direction is equal to, well, we had our first component, which was the derivative with respect to time in the control volume, right? And this is going to be 0 because I'm just going to write it down, but it's rho d volume. But this guy really is 0 because the situation is steady. Let's just keep it there just to remind ourselves. And we have this other component, which is the surface one. So I'm just writing it out fully, but we know that this is going to simplify quite a bit. This is in the control surface. So this is just, in this case, the flow of momentum. And the flow of momentum, there's only one flow of momentum, minus rho a v squared, the velocity squared of that jet, is a momentum outflow. This guy. The minus sign is because the velocity points outward. Negative in the z direction, basically. We're looking at the z direction, so I just keep yes, a question. This row, or the second, the unit normal. That's why we always want to draw our control surface perpendicular to the flow, because that makes it very easy. We know that we don't have to get any angle involved in this dot product here, v dot n. If we choose our control surface to be perpendicular to the velocity, this is very easy. We just need to keep track of the sign. That's it. So we have a momentum outflow, and that's we're done. So now we can do a sum of forces. We haven't. This is the force, fluid force, but we have weight as well. So the weight of the rocket. So now let's do the complete sum of forces. And we have, and also of course the reaction and the beam. So we have sum of forces in the z direction equal to minus FB, because pointing downwards here in the z direction, minus the weight also pointing downwards in the z direction, and this has to be equal to, well, mass times, do we have any mass for the rocket? Mass of the rocket, I do have it here, but I didn't write it down. Mass of the rocket is equal to 40 grams. This is not G, this is grams, the unit. So force of the beam is what we want to find. But weight, we know, is minus mg. The mass is given. And that from the momentum equation now, minus F B minus mg is the sum of forces equal to the momentum rho, the momentum outflow rho a v squared. So basically we combine these two things. So now we can obtain the FB, but I've run out of space. Where shall I do that? Let me maybe do it here. In green, we can get now that force FB, the force at the beam is equal to rho a v squared minus, minus rho a v squared, yes, minus mg. That is equal to, I can put the values now, rho 0.5 kilograms meter cube. The area, well, we have the diameter of the jet, so we can calculate the area, pi fourth times diameter cube, squared, 1 centimeter. So we change it to meters immediately. 1 centimeter is 0.01 meters, and that's squared, times v squared. What's v? V is 450 meters per second. V squared minus m. M is 40 grams, so I write that in kilograms already. 40 grams is 0.04 kilograms. And the acceleration of gravity, 9.8. Oh, I don't have space. Meters square seconds. Okay, it fits there. So now we have everything. We can put those numbers in the calculator. Everything is known. So FB is known here, and I've already computed this, and we have 7.56 Newton pointing upwards. That's the force on the beam. On the control volume, it points downwards. On the beam, it points upwards. So we've simply applied here just conservation of momentum to obtain this result. This is a typical sort of application. Any questions? Yes, I see a question back there.
What is the area of
The area of the jet. It's a very, very classic application of the momentum equation, of course. Very useful. Okay. Oh, more space. Second type of problem, the second application that we have is nozzles. What do I mean by nozzles? Well, we have so these are types of free jets. Remember, the rocket is a free jet, and the nozzle is also a free jet. So a nozzle is a flow device which is used to accelerate the fluid by reducing the cross section. Simple as that. Like in the case of the fire hose that we were talking about. So again, the tips for nozzles, we assume uniform velocity in the cross section. All the momentum flows are going to be m dot v, so it's going to be the easy type. The nozzle exerts to atmospheric pressure, so again we use gauge pressure. so that we can write the pressure at the exit equals 0, and that simplifies our force balance. And the additional element compared to the previous example is going to be that we're going to use Bernoulli's equation to obtain the interior pressure. So for example, this is a nozzle. Like I said, just a device that accelerates fluid by reducing the cross section. So here we have a nozzle, fluid enters here and exits as a free jet. Out there, fluid everywhere, okay. So normally a nozzle will have some sort of way to be pinned together to the rest of the planet, and these things are called usually flanges. So usually some round, or two little plates that are pinned, pinned together by bolts. Here, flanges, or you could have a human holding it, like in the case of the fire hose. But in this case, we're going to look at flanges, these sort of mechanical devices to fix the nozzle to one particular location. So let's consider. Yes. Well, let's look at that. Basically, if I draw a control volume around this thing, whatever is inside that control volume is like a black box. I don't see what's happening, right? And as long as I know the momentum that comes in and the momentum that goes out, you see I'm going to get the same result, regardless of what's happening inside. Okay. So let's put some numbers here so we can calculate this. Let's suppose an inlet. In this case, we are given exhaust. In this particular numeric example that we're going to do, we're given an inlet pressure P1. So I'm calling this guy 1, this section 1, and this section 2. Inlet pressure P1 is equal to 105 kilopascal. This is absolute. This is what the numeric example gives us. The exhaust pressure is at atmospheric pressure 101.3 kilopascal. We have an inlet diameter, and that's 60 millimeters, and we have an outlet diameter of 10 millimeters, and we have density rho. This is just going to be air, 1.22 kilograms per meter cubed. And in this case, the nozzle is connected to a supply of air by some flanges. Yes? No difference, just choice of words. This is the no. This is in general the tips for problems, but in this particular example, you're given that, okay? Because you're asked to calculate the force. Yes. Yes. P2 at the atmosphere. Because in this case, you're not given what you're not. This is what you're given, okay? In this particular example, but what you don't know is the airspeed at the exit and the force required on the flanges. the force to keep this in place. Of course, we're going to make the assumptions of inviscid flow, constant density. Let's write those down, actually, just so that we are clear on that. Rho equals constant, inviscid, steady. That's the minimum things that we need to assume. So the first step, as before, is to choose a control volume. And draw force diagrams and momentum. So that's not too hard. Let's actually decide to draw our control volume right across the flanges where there's going to be some bolts holding this together, and include the whole nozzle and perpendicularly cut the jet at the exit. So what do we have? We have this force that we need to calculate, first of all, and it's going to apply all around this plate, but let's just call it F, some sort of resultant force. But we also have a pressure force in this case. This problem has, in addition, P1 times area. Because the pressure on this side is not atmospheric, it's different than atmospheric, okay? On this control volume. In the previous control volume, it enclosed the whole rocket and the jet was at atmospheric pressure. So the whole surface of the control volume was at atmospheric pressure. But in this case, there's a part of the control surface that is at a different pressure. So we have to consider the pressure forces. We don't have any stresses, shear stresses, because it's inviscid and there are no other, there are no forces tangential to our control surface. There's only the pressure force. And of course, the force at the flanges. And what are our momentum fluxes? I'm going to erase this, which is in my way here, and this also. And I'm going to use the green color to draw the momentum fluxes. And the momentum fluxes are going to be simply here m dot v2 and here m dot v1. That's all the momentum fluxes that we need to consider. So I'll draw forces and momentum and choose my control volume. So momentum inflow and outflow in the, say, x direction. Let's call this x direction. And force due to pressure and the forces at the flanges. We've set up the problem now. So now we can apply Bernoulli's equation. We still have to apply Bernoulli's equation in this case and continuity equation between sections 1 and 2. Continuity equation, I mean conservation of mass. It's just another name for it. Between sections 1 and 2. Okay, Bernoulli tells me that P1 plus 1/2 rho V1 squared plus gamma Z1 is equal to P2 plus 1/2 rho V2 squared plus gamma Z2. And of course the 2Z, the two elevations are equal, so this guy cancels out immediately. I don't have to worry about that. And P2 is equal to 0 because this is atmospheric. And so we can find P1. We need to put P1 in terms of gauge pressure because that's why we can get rid of this guy. So P1 is going to be equal to 105 minus 101.3 Pascal. So that's equal to 3.7. Oh, yeah, 3.7. 3.7 Pascal. So this, we want to write this in gauge pressure so that this was going to be equal to 0 in gauge, right? We have one less thing. Yes. Kilopascal. Yes, thank you. Thanks very much. Gauge, of course, gauge. So what do we have? We have pressure, basically P1 in terms of V1 and V2. We don't know either one. So now that's where we have to apply continuity. Yes.
You're just saying gamma V1 cancels, gamma V2 cancels because there's no appreciable gradient.
Z1 equal to Z2. It's just a small little device that displays pointing outwards. There's no difference in elevation between these 2 points. It's just the nozzle, right? If I had a big system with pipes going up and down, then I'd have to consider Z. But in this case, it's just the nozzle. It's all at the same elevation. Okay, so far? Now we're going to use continuity because we have too many unknowns. We have P1, V1, rho 1, so we need more equations. We're going to use continuity, and I'm going to clear up here to have more space. Again, I don't know. So the reason I do is because I do that like that because I want to keep this equation at the bottom, and so if I clear the slide completely, I won't have that. I also won't have the drawing, but you have your own notes to see what the numeric values that we need to use are, and so now we can continue here. So now what is it? I apply continuity. So continuity, in this case, is a case of steady one-dimensional flow. Steady one-dimensional flow, one inlet, one outlet, then it's the simplest possible case, and we have A1, V1 is equal to A2, V2. That's our simplest version of the conservation of mass. Continuity is the same as conservation of mass, just another name. So that means that I could now write this perhaps in terms of the diameters, and I could just say like, let me use the diameters and write, because then the pi's cancel out, right, from the areas, and so I could write V1 D1 squared equal to V2, so 1 D2 squared. So what we're going to do is express V1 in terms of V2 so that we can put it back in this other equation here. I have, let me write this guy, P1 from here. This is from Bernoulli's equation. P1 plus 1/2 rho V1 squared equals 1/2 rho V2 squared. And so here I can put, for V1, I can put V2 times D2 squared divided by D1 squared. Right? So now we have only V2 is unknown. Remember, pressure was given. So only V2 is unknown now in the rest of the equation. So I can express now V2 in terms of P1, which is given in the problem. And now I'm just going to skip to my final answer because this is just algebra and you see where it comes from and you can check it. I have written, I'm not going to bother with every step. V2 now, as you see, that is it's going to be all of this squared, of course, in here. V1 is squared, so all of that is squared. So I can solve for V squared and then take square root. So you can see this is a square root of, I'm going to write the whole thing is 2 P1 divided by rho 1 minus D2 over D1. This is squared and squared again, so it's to the 4th power. And here's the expression for V2 in terms of P1. P1 is known. I can put all the numbers that we have for that problem in there. And I'm going to skip that final numeric step, which you can check in your own time, because we are coming to the end of the lecture time, and just write what the result should be, and you can check it. 77.9 meters per second is the result I obtained by putting everything is known inside here. That is the outlet velocity. Now we can get the inlet velocity from, of course, we have this relationship here. And so if we know V2, we can now get V1. And now we have everything. Is that clear? And we have come to the end of our lecture time today, but next class we're going to continue with this example. We're not finished because we have to apply the momentum equation to obtain the forces. We have just been able to get the velocities at this point. So we'll continue and do more examples next class. Thank you.